The College of New Jersey. I
Hello,
spent
everyone.
40 years, I
Hello.
spent 40 years down up in New Jersey, very familiar with TCNJ.
Oh, thank you. That's great. So my name is Orlando Hernandez. I'm with the College of New Jersey, the Department of Electrical and Computer Engineering. And this work is regards a fully integrated VLSI circulator for the ISM band of 915 megahertz, which is applicable to RFID and IoT. So just some quick background. A circulator is a three-port device that is generally used and mostly used to connect a bidirectional antenna to the transmitter and the receiver. And the idea is that via directionality, the signals that are going to be transmitted go out the antenna, but they don't feed back into the receiver. And the signals that come through the antenna go to the receiver and don't interfere with the transmitter. So normally these circulators are passive, they're bulky, and they are expensive. So this work has to do with an active circulator made out of modular amplifiers and some history and motivation for how we got here, because this is just a small piece in a bigger project. We started working with a client that wanted to build a very inexpensive IoT device, specifically RFID related, and for the consumer space. And what they found is that chips that had to do with this technology, they were all basically a monopoly of some semiconductor company in Europe, and they were very expensive. So expensive would be like $40 for the chip, and the company had a circuit around it. So they tasked us to come up with an RFID transceiver that used off-the-shelf OOP type of transceivers that didn't know anything about RFID, and that we would apply sort of a software-defined radio paradigm to do the RFID transceiver. So we did that, and in the process, we had still to solve the problem of the circulator. So we actually implemented a very simple and modular circulator on boards with chips that had match P and N channel transistors, and that worked very well. So then we took it one step further and said, why not then design an fully integrated active circulator that uses the same topology and the same ideas. And that's how we got to this circulator, which basically is three amplifiers with an appropriate input coupling network, where, of course, with the directionality in this picture, that we get a signal from one port and it goes out the next, and it doesn't go out the next over. So the topology that we chose is a differential current loaded, so MOS differential amplifier loaded by a PMOS current mirror, and they are exactly the same with an appropriate CR coupling network, or it's really a pi. It's CO, RO, and then another RC into the next amplifier, and that is shown on the left, and then the small signal model is shown on the right, and all the derivations are on the paper. But the main thing, sort of the punchline, is that when you analyze this amplifier and account for the loading and make the reasonable assumption that the 1 over GM of this transistor, which is very important here, on the positive input of the differential amplifier, if you make the assumption that 1 over this GM is much smaller than the output resistance of this diode configured p-channel transistor, if you make that assumption, then you can come up with this governing condition for this this ring to work, because it does have some oscillatory characteristics, so you have to make sure that you have the right gain margin and phase margins for it not to oscillate at its natural frequency and work at the frequency that you want it to work, which in our case is centered around 915 megahertz. So we derived this governing condition or equation, and then designed the amplifier appropriately with these parameters, and we check here that indeed we are greater than 1. So we also characterize the transistors that are in the library for the process that we are using. It's a 45 nanometer process, and we were able to characterize things that we needed to design the amplifier, like the threshold of the transistors, the K primes, and also the early voltages. So we got those, and this table here shows the parameters that we ended up choosing and building our design around. So this, because this is a very well, it's a 45 nanometer technology. The VDD that we use is only 0.9 volts, so it's low VDD with a bias current of only 200 microamps, and all the transistors are the same. Even P and N channels are the same. We found that we didn't have to account for the lower mobility of holes, so we didn't have to make the P channels larger compared to the N channels to account for that. All the transistors are the same. They have a width to length ratio of 36. Here we can check that 1/GM is certainly much lower than the output resistance of the transistors, the N channel and the P channel. So our derivation holds with respect to that. And then each amplifier stage has about a gain of 6, but that's what is needed. So when you take the loading effects into account, you come up with a gain of 1 on the passing port. So this is our layout. You can see here it's very modular. The amplifier is here. This area here is the bias generator for the amplifier. Since we had a space, and to make it more modular, we actually replicated the bias generator, although we could have used only a single bias generator for all 3 amplifiers, but we replicated the bias generator. And these are resistors and capacitors over here. So that is our fully integrated circuit with the three amplifiers and the coupling networks. Post layout simulations show very good results. Where we have, in this case, the signal is being input in port 1, and it comes out port 2, and then it's rejected at port 3. And we also saw very good symmetry from port to port. So if we look at the results, when we put the signal in port 2, comes out port 3, rejected on port 1, and then if we put the signal in port 3, comes out in port 1 and rejected on port 2. The frequency response shows the same thing as the transient analysis. Here's the signal into port 1 and out port 2 and rejected on port 3. And it also shows very acceptable bandwidth from about 300 megahertz to I think 1.3 gigahertz. So since we're targeting the ISM band, specifically at 915 megahertz, that is we were very happy about that bandwidth. So again, the frequency response on all 3 cases shows the same thing, where we are putting the signal in port 3, out on port, we're putting the signal in port 2, out on port 3, rejected on port 1, and finally putting the signal into port 3, passing to port 1 and redirecting on port 2. System level performance parameters. So this for us was important. We have a return loss. Actually, we have almost no return loss. That was important to us, so that the signal that came in the input port will go out the output port, the desired output port on change. The isolation on the stop port is very good. It's greater than 17 dB of isolation, which is good. It's not the best, but it's acceptable. And also the bandwidth, power dissipation about 2 milliwatts. Very small area because we're using a standard 45 nanometer CMOS process, about 0.001 millimeters square, and an efficiency of about 20%. That for active circulators is very good. So we did.
Sorry for the interruption. Okay, sorry for the interruption, Orlando, but you have a little under 2 minutes left.
Thank you, sir. And so the efficiency is greater than 20%, which is actually very good for active circulators. And so yeah, that was we did look in the literature, and it fares very well, and also even better than lots of active circulators that have been reported in the literature. So it is really novel, and the performance is high in terms of compactness, low power, high efficiency. It is suitable for time division duplex operation and transceivers, minimal passport losses, so and suitable stop port isolation. And again, this is an excellent circuit for integrated RFID and IoT applications for U.S.-safe 915-MHz ISM band. And it's been validated with actual circuits in hardware on a board. So the only thing that hasn't been addressed, that wasn't addressed, was the IO impedance matching, but that can be addressed with the BALM, and we may add that to this integrated circuit in the future, both on the input and outputs, or in all ports essentially, to address the impedance matching. So that will be the next thing to add to this integrated circuit. So with that, yes, thank you so much, and I'll take any questions from the audience.
Any questions, guys? So the only question I have is, obviously this is a continuing area of research for you. So what's next?
Well, the BALM, adding BALM to the ports, that would be the next thing. And also, we feel very comfortable with the work that we did before at the board level with this match transistor chips that we obtained. Very fast MOSFETs, very low gate capacitances. But there are some programs that we are looking into to actually build the chip and get funding to do that, and actually be able to measure and use this actual chip that is presented here in real hardware. So those are two areas that we want to pursue.
Wonderful. So I guess thank you.